They said it would disappear. By now 3i Atlas should have slipped behind the sun, fading into the depths of space forgotten. But it didn't. It lingered. And in that persistence something shifted. Its brightness, its speed, its silence. Now, on December 15, 2025, Earth and 3i Atlas will align in a way never seen before in recorded history. Every telescope is trained on it. Every signal is being analyzed because it may just do something no one is prepared for. NASA calls it a harmless interstellar visitor. But what if the truth is something else? What if it's waiting for the right moment? Stay with me by the end of this story. You'll understand why some believe that moment won't just reshape our understanding of the cosmos, it could reshape us. The countdown is real, and it's already begun. If this mystery has you as intrigued as it has me, don't stay in the dark. Hit like and subscribe. Trust me, you won't want to miss what happens next as it unfolds in real time. Drop a comment letting me know where you're tuning in from, what time it is where you are, and whether you think we're being told the full truth about these world-changing discoveries. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even in your group chats. You're the reason we can continue pursuing stories like this. Thank you for your support. Part 1. The countdown begins. Imagine this. It's a clear night in late October 2025. You're standing in your backyard gazing up at the stars, everything calm, peaceful, normal. But out there in the depths of space, something is moving faster than any man-made object we've ever launched, headed toward an appointment none of us planned. NASA says don't worry. The European Space Agency calls it routine. They assure us that December 15th will just be another day. But here's the part they're not telling you in their press releases. Here's what's keeping amateur astronomers up at night, refreshing their telescope feeds, double-checking their calculations again and again. Something about 3i Atlas is refusing to follow the script. So far, we've only detected 3 interstellar objects passing through our solar neighborhood. The first, Oumuamua, in 2017, was that cigar-shaped visitor that accelerated in ways gravity alone couldn't explain. Scientists are still debating its true nature. The second was Boris in 2019, which behaved more like a typical comet but raised questions about its origins and what it carried. Now we have 3i Atlas, the third interstellar visitor, and it's not acting like the others. On July 1, 2025, the Atlas telescope in Chile spotted something unusual. In its survey images, a faint smudge of light moving against the backdrop of stars. Within days, astronomers calculated its trajectory and realized what they were seeing. This object wasn't bound to our sun. Its orbit was hyperbolic, meaning it came from somewhere else, somewhere in the vast space between stars, and it would eventually return there. The numbers were staggering. It was moving at roughly 60 kilometers, with an eccentricity between 6.14 and 6.20, far beyond the threshold that separates solar-bound objects from interstellar wanderers. It was coming in fast and would leave even faster. NASA and ESA quickly published the basic facts. Perihelion, the closest approach to the Sun, would occur around October 30th at about 136 to 1.4 astronomical units. That's inside Earth's orbit, closer than Mars, but still a safe distance away. Then 3i Atlas would swing back out, passing closest to Earth in mid to late December at roughly 1.8 astronomical units, about 168 million kilometers away. Nothing to worry about, they said. Just another visitor passing through. But then the whispers started. Astronomy forums lit up. Amateur astronomers shared observations that didn't match the official predictions. Someone claimed they measured the object's position and found it offset by several arc minutes from where JPL Horizon said it should be. Another posted photometry data showing brightness variations that didn't fit the standard models for comet activity. A third noted that the tail seemed to be pointing in an unexpected direction, as though the object was being pushed by forces the models hadn't accounted for. Were these observations real? Or were they just calibration errors? Atmospheric distortion, wishful thinking? That's the question, because if 3i Atlas really is deviating from its predicted path just slightly, then everything we think we know about its December flyby might be wrong. And if the deviations are systematic, accumulating over time, then the geometry of December 15th might look very different from what the official ephemerides are telling us. Now let me paint a picture of what December 15th might look like in terms of celestial mechanics. By that date, 3i Atlas will have passed perihelion more than 6 weeks earlier. It will be moving away from the Sun, but still relatively close to Earth. More importantly, the alignment will be nearly perfect. If you draw a line from the Sun through 3i Atlas, it will point almost directly at Earth. We'll be downstream of the comet, sitting in whatever wake it leaves behind. If 3i Atlas has developed a tail of ionized particles, if it's been releasing gas and dust heated by its close pass to the Sun, then Earth will be directly in the path of that material. At 1.6 to 1.8 astronomical units away, it's still a considerable distance, but it's close enough for certain effects to propagate. Radio waves would reach us in about 8 to 9 minutes. Charged particles carried by the solar wind could drift across that gap in days or weeks. Even gravitational influences, though infinitesimally weak, could be measurable. So here's the question no one seems to want to ask out loud. What if December 15th isn't nothing? What if the alignment triggers something we didn't anticipate? I'm not talking about an impact. 3I Atlas is nowhere near close enough for that. I'm talking about something subtler, an electromagnetic pulse, a burst of radio waves, a sudden brightening or dimming, a glitch in our satellites, an unexplained aurora at latitudes where auroras don't usually appear, something small enough to be dismissed as coincidence but strange enough to make you wonder. The official story is clear and confident. 3I Atlas poses no threat. The trajectory is well understood. It's just a comet, albeit one from another star system. December 15th will come and go without incident, but confidence and certainty aren't the same thing. And in the quiet spaces between the press releases and public statements, there's room for doubt, room for questions, room for the possibility that we're about to witness something unprecedented, and we don't even know it yet. Part 2. The object that refuses to follow the rules. The official discovery date was July 1st, 2025, but the story of 3I Atlas actually begins much earlier, long before that. When researchers sifted through archival data from the TESS Space Telescope, they found something unexpected. The comet was already active. Even when it was still out near 6.5 astronomical units from the Sun beyond Jupiter's orbit, it was producing a visible coma of gas and dust. Comets aren't supposed to behave this way. The conventional model says that comets remain frozen and inert until they get close enough to the Sun for solar radiation to start sublimating their ices. But 3I Atlas was already awake, shedding material, while still in the cold outer reaches of the solar system. This pre-discovery activity tells us something important. This object is different. Either it's made of unusually volatile materials that sublimate at lower temperatures than normal comets, or it has an internal heat source we don't yet understand, or perhaps it's not entirely natural. Those are the possibilities, and each one carries significant implications. Let's talk about the numbers that matter. Observations from the Hubble Space Telescope place constraints on the size of 3I Atlas. The nucleus, the solid core of the comet, is somewhere between 0.44 kilometers and 5.6 kilometers in diameter. That's a huge range of uncertainty. It could be a relatively small chunk of ice and rock, or it could be something much larger. The size matters because it determines how much material the comet can release, how strong its gravity is, and how much energy it might contain if something inside is generating heat. The Gemini Observatory tracked 3I Atlas through perihelion and confirmed what Atlas had seen: the hyperbolic trajectory, the extreme velocity. But Gemini also provided something new: polarimetric data. When light reflects off the comet's coma, it becomes polarized in a way that depends on the size and composition of the dust particles. 3I Atlas showed something strange: extreme negative polarization. This kind of signature suggests dust grains with unusual optical properties, or a composition that doesn't match any known comet from our solar system. Now we come to the part that's causing all the speculation: the amateur observations. Citizen scientists with backyard telescopes and CCD cameras have been tracking objects like 3I Atlas and sharing their data online. Starting in October, some of these observers began reporting discrepancies. One group claimed they measured the comet's right ascension and declination coordinates and found offsets of several arc minutes compared to the predicted ephemeris. Another reported brightness curves that didn't match the expected decline as the comet moved away from the Sun. A third noticed variations in the tail structure, suggesting non-gravitational accelerations. Here's where it gets tricky. Amateur observations are valuable, but they're also prone to error. Atmospheric refraction can bend light and shift apparent positions. Calibration mistakes can throw off photometry. Telescope tracking errors can create false motion. So when someone reports an arc-minute offset, we have to ask, is that real, or is it just noise? The official ephemeris from JPL Horizons includes uncertainty intervals. Small deviations are expected and normal, but what if the deviations aren't small? What if they're systematic and growing? Let's do the math. An arc-minute is 1/60th of a degree. At a distance of 1.8 astronomical units, 1 arc-minute of angular offset corresponds to a lateral displacement of about 780 kilometers. That's not trivial. If 3I Atlas is really 780 kilometers off course from where it should be, that represents a significant unmodeled acceleration. Over the course of weeks, a tiny constant acceleration could accumulate into exactly that kind of displacement. What could cause such an acceleration? The most likely answer is asymmetric outgassing. When ice sublimates on one side of the comet's nucleus, it creates a jet that pushes the nucleus in the opposite direction. This is a known phenomenon, and we've observed it in dozens of comets. But the magnitude matters. For 3I Atlas to deviate by hundreds of kilometers, the outgassing would have to be unusually strong, or unusually one-sided. And if that's the case, then the comet is more active, more volatile, more unpredictable than the models assumed. Or there's another possibility. What if the deviations aren't caused by outgassing at all? What if something else is at work? A plasma interaction with the solar wind, a gravitational perturbation from an unseen mass, a propulsion system. Yes, I said it. The idea sounds absurd, but Oumuamua taught us that sometimes absurd ideas deserve serious consideration. When an object doesn't behave the way physics says it should, you have two choices. Either your physics is incomplete, or the object is not what you think it is. NASA's official position remains unchanged. 3I Atlas is a comet, its trajectory is well understood, and the approach to Earth in December poses no risk. But here's what they're not saying. They're not releasing daily updates on the object's position. They're not publishing detailed photometry. They're not addressing the amateur observations that claim to see anomalies. That silence could mean nothing. It could mean they're busy with other priorities. Or it could mean they're waiting to see if the anomalies resolve themselves before making any public statements. December 15th is coming. Whether we're ready or not, the geometry is set. Earth will be in alignment with the Sun, and 3I Atlas will be downstream of its tail directly in the path of whatever it's been releasing since perihelion. If the amateur observations are correct, if the deviations are real, then the object might be closer than expected, or oriented differently than predicted. And if that's the case, the alignment might be tighter, more precise, and more significant than anyone is acknowledging. The question isn't whether something will happen, the question is whether we'll notice when it does. Part 3. The geometry of convergence. Imagine a clock. The Sun is at the center and the planets orbit like hands sweeping around the dial. Now imagine a visitor from outside a piece of interstellar debris that doesn't care about our orderly clockwork. It cuts across the face of the clock at an angle moving faster than anything bound to the Sun's gravity. That's 3I Atlas, and on December 15, 2025, the hands of the clock will point in just the right direction for something unusual to happen. Let me be precise about the geometry. Perihelion occurred around October 30th, when 3I Atlas made its closest approach to the Sun at approximately 1.36 astronomical units. That's about 204 million kilometers. Close enough for solar radiation to heat the nucleus, intensely vaporizing ices, releasing gases, and creating the comb and tail that make comets visible. For several weeks after perihelion, the comet has been moving outward, climbing back up the gravity well, heading toward its eventual escape from the solar system. By December 15th, 3I Atlas will be at roughly 1.6 to 1.8 astronomical units from both the Sun and Earth. But distance isn't the only thing that matters. What matters is alignment. On that date, if you draw a straight line from the Sun through the comet, it points almost directly at Earth. We're not just nearby, we're downstream. We're in the zone where the comet's tail should be. Comet tails come in two types. Dust tails made of microscopic particles pushed outward by solar radiation pressure, and ion tails made of charged particles ionized by ultraviolet light from the Sun. These tails point directly away from the Sun, pushed by the solar wind. If 3I Atlas has an active ion tail, and if that tail is oriented correctly, then on December 15th Earth will pass through it. Now 1.6 astronomical units might sound like a lot of space, huh? That's about 240 million kilometers, but consider what can propagate across that distance. Radio waves travel at the speed of light, covering the gap in about 13 minutes. Charged particles in the solar wind move at several hundred kilometers per second, taking days to weeks to drift from the comet to Earth. Even relatively slow-moving dust particles, if they're small enough and charged enough, can be carried along by electromagnetic forces. The question isn't whether anything from 3I Atlas can reach us. The question is what reaches us and what effect will it have when it arrives. Let's talk about coupling. That's the physics term for how two systems interact and exchange energy. Earth has a magnetosphere, a protective bubble of magnetic field that shields us from most of the charged particle radiation streaming off the Sun. When that radiation hits the magnetosphere, it can cause disturbances. Magnetic field lines reconnect, electric currents flow in the upper atmosphere, and we see auroras. We experience geomagnetic storms that can disrupt satellites and power grids. Now imagine that instead of the usual solar wind, the magnetosphere encounters a stream of ionized particles from a comet's tail. Would it behave differently? Would the coupling be stronger or weaker? Would we see effects that don't fit the normal patterns? The distances involved are significant. At 1.6 astronomical units, the density of the solar wind is much lower than it is near Earth. The magnetic field carried by the solar wind is also weaker, but a comet's ion tail can contain its own magnetic structures, twisted loops and filaments created by the interaction between the outflowing gas and the interplanetary field. If Earth's magnetosphere encounters one of those structures even briefly, it could trigger localized disturbances. Auroras at unusual latitudes, radio blackouts, satellite telemetry glitches. Nothing catastrophic, nothing that would make headlines under normal circumstances, but enough to be noticed, enough to raise questions. There's another possibility. What if the alignment isn't just about geometry? What if it's about timing? Suppose that something about 3I Atlas's passage through perihelion triggered an event, maybe a release of stored energy, a burst of activity, or a change in the object's behavior. And suppose that event produced something that propagates outward at a specific speed timed to arrive at Earth's location on December 15th. That's pure speculation, I'll admit, but it's speculation grounded in physics. If an object releases electromagnetic radiation, it travels at light speed. If it ejects particles, they travel at whatever velocity they were given. If it creates a disturbance in the interplanetary medium, that disturbance propagates as a wave. The timing could be coincidental, or it could be deliberate. This is where mainstream scientists shake their heads and walk away. They'll tell you there's no mechanism for a comet to produce a targeted effect. They'll tell you that any release of energy would be isotropic spreading in all directions, not focused on Earth. They'll tell you that the alignment is meaningless, a purely geometric coincidence that humans are pattern matching into significance. And they're probably right. Probably. But here's what keeps me up at night. We've never had an interstellar comet pass through our solar system before, in the era of modern astronomy. Oumuamua was the first, but it didn't have a visible tail. Boris was the second, but its geometry was different. 3i Atlas is giving us a scenario. We've never tested an interstellar visitor with an active coma and tail passing close enough to interact with Earth's magnetosphere, aligned in a way that puts us directly in its outflow path. We have models and predictions, sure, but models are only as good as the data they're built on, and we have no data for this specific situation. December 15th is a test, not one we designed or wanted, but a test nonetheless. If nothing happens, the models are validated and the skeptics are proven right. If something happens, even something small, we'll learn that our understanding of cometary interactions was incomplete. Either way, we learn. But I can't help wondering which outcome would be more unsettling. The confirmation that we understand everything, or the revelation that we've been missing something all along. Part 4. 5 scenarios nobody wants to consider. I'm going to walk you through 5 hypotheses. 5 scenarios that could in theory produce observable effects on December 15th. I want to be clear from the start, none of these are mainstream scientific predictions. These are thought experiments. They're the kinds of ideas that get discussed in hushed tones after conference sessions or kicked around in late-night forum threads by people who enjoy pushing boundaries. But they're worth examining because even the most speculative hypothesis can teach us something about what's possible and what's not. Scenario 1. The silent activation event. Here's the premise. 3i Atlas has been traveling through interstellar space for millions of years, cold and dormant. Then it enters our solar system, approaches the sun, and heats up for the first time in its long history. That heating triggers something, maybe a chemical reaction deep inside the nucleus. Maybe it's the sublimation of a volatile compound that was stable in interstellar space but unstable in sunlight. Maybe it's something more exotic, a stored energy source that we don't have a name for yet. Whatever it is, it activates at perihelion, and that activation produces an output, a burst of electromagnetic radiation, a release of particles, something that propagates outward in a directed beam, or a spreading wave. If the timing and orientation are right, that output reaches Earth on December 15th. What would we see? It depends on the nature of the output. If it's radio waves, we detect a transient signal, possibly at frequencies we're not normally monitoring. If it's high-energy particles, we'd see an uptick in cosmic ray detectors and satellite radiation monitors. If it's an electromagnetic pulse, we might see temporary disruptions in communications or power systems. None of these would be catastrophic, but they'd be noticeable and they'd be unexplained by any conventional model. Scenario 2. Gravitational and plasma resonance. This one's subtler. The idea is that the alignment on December 15th creates a configuration where Earth's magnetosphere becomes unusually sensitive to disturbances in the interplanetary medium. It's like resonance in a musical instrument. Hit the right frequency and the whole thing vibrates. Normally, Earth's magnetosphere is robust and well shielded, but under certain conditions, when the solar wind has just the right velocity and magnetic orientation, even a small perturbation can trigger a large response. Now suppose 3i Atlas's ion tail carries its own magnetic structures, and those structures interact with Earth's magnetic field in a way that hits that resonance point. The result would be an enhanced geomagnetic response. Auroras would appear at latitudes where they're not normally visible. Ground-based magnetometers would register anomalous fluctuations. Satellites in certain orbits might experience increased drag or electronic interference. Again, nothing apocalyptic, but enough to show up in the data. Enough to make scientists wonder what the hell just happened. Scenario 3. Fragmentation and outgassing burst. Comets are fragile things. They're not solid rocks. They're piles of ice and dust held together by weak gravity and even weaker cohesion. Sometimes they break apart, especially after a close pass of the sun when thermal stresses crack the nucleus. If 3i Atlas underwent fragmentation around perihelion, the pieces would continue on slightly different trajectories. Some of those pieces might outgas more vigorously than the main nucleus, releasing bursts of gas and dust that create temporary enhancements in the coma. If one of those bursts happens to occur just as the geometry aligns on December 15th, Earth might find itself passing through a denser than expected cloud of cometary debris. Satellites in low Earth orbit would experience increased atmospheric drag. There might be an uptick in meteor observations as dust grains burn up in the upper atmosphere. Optical telescopes might detect a sudden brightening or a change in the tail structure. It wouldn't last long, hours, maybe days. But for that brief window, 3i Atlas would be behaving in ways the models didn't predict. Scenario 4. The probe. Hypothesis. Now we're venturing into territory that most astronomers refuse to acknowledge in public, but since we're here, let's go all the way. Suppose 3i Atlas is not entirely natural. Suppose it contains embedded within its icy nucleus something artificial, a probe, a relay, a dormant machine that's been coasting through space for eons waiting for the right conditions to activate. It doesn't have to be large. A device the size of a car buried inside a comet nucleus several kilometers across would be invisible to our telescopes. And it doesn't have to be active all the time. Maybe it wakes up when it detects the presence of a star. Maybe it uses solar radiation to recharge its power systems. Maybe it waits until it's in a specific geometric configuration like the alignment on December 15th, and then transmits a signal, a beacon, a packet of information sent toward a particular point in space. If Earth happens to lie along the transmission path, we'd receive that signal. It might be at radio frequencies, optical, or something else entirely. It might be modulated in a way that stands out clearly from background noise, or it might be subtle enough that only dedicated monitoring would catch it. SETI researchers dream of scenarios like this, a technosignature delivered to our doorstep by a wandering interstellar probe. It's the ultimate long shot, but it's not physically impossible. Scenario 5. The optical reflection phenomenon. This one's almost mundane compared to the others, but it's worth mentioning. Suppose that on December 15th, the angle between the Sun 3I Atlas and Earth reaches a specific value that maximizes the reflection of sunlight off the comet's coma. Think of it like a glint, the way sunlight reflects off an airplane's fuselage at just the right angle, and you see a brilliant flash. If the dust particles in the coma have the right size and composition, and if they're arranged in a particular configuration, the comet might suddenly brighten by several magnitudes for a few hours. Observers on Earth would see a temporary increase in brightness. Social media would light up with reports of a strange glow in the sky. Amateur astronomers would scramble to capture images, and then it would fade, returning to normal brightness as the geometry changed. Nothing dangerous, but eerie. Unsettling. The kind of thing that makes people feel like the universe is sending a message even when it's just physics playing tricks with light. These 5 scenarios span a range from conventional physics to wild speculation. What they have in common is that they're all technically possible. The probabilities vary. Some are vanishingly unlikely. Others are merely improbable, but none of them violate the known laws of nature. And that's what makes December 15th interesting. It's not that we expect any of these scenarios to occur, it's that we can't completely rule them out. And in the gap between expectation and certainty, there's room for surprise. Part 5. The architecture of institutional silence. NASA's official statement on 3I Atlas is brief and confident the object poses no threat to Earth. Its trajectory is well understood. The December approach is a routine event that will be monitored by standard observational protocols. Nothing to see here, move along. And maybe they're right. Maybe there really is nothing to see. But there's a curious pattern in how information about 3I Atlas has been managed, and that pattern deserves attention. Let's start with the basics. When Oumuamua was discovered in 2017, it took weeks for the scientific community to realize it was interstellar. Initial observations suggested a normal asteroid. Only after detailed orbit calculations did astronomers understand they were looking at something from beyond our solar system. The announcement, when it came, generated enormous public interest: news articles, documentary segments, even congressional inquiries. Everyone wanted to know what Oumuamua was and where it came from. With 3I Atlas, the process has been different. The interstellar nature of the object was recognized almost immediately. The initial discovery announcement mentioned the hyperbolic orbit, but after that the flow of information slowed to a trickle. There have been no major press briefings, no detailed scientific papers in high-profile journals, and no follow-up observations released to the public. The object is being tracked, certainly data is being collected, but it's not being shared with the same transparency that accompanied Oumuamua. Why the difference? One possibility is that 3I Atlas is simply less interesting from a scientific standpoint. It appears to be a comet, albeit one from another star system. Comets are common. We've studied hundreds of them. Maybe there's just not much new to say. But that explanation doesn't quite fit. The pre-discovery activity at large heliocentric distances is unusual. The extreme negative polarization is unusual. The amateur reports of trajectory and brightness anomalies are unusual. There's plenty of interesting science here. So why the quiet? Another possibility is caution. Space agencies learned from Oumuamua that announcing surprising results too early can lead to a media frenzy that spirals out of control. Remember how quickly Oumuamua went from asteroid to possible alien probe. In the public imagination, NASA might be deliberately downplaying 3I Atlas to avoid a repeat of that circus. Better to wait until the data is complete, and the interpretation is certain before making any statements that could be misunderstood or sensationalized. But there's a third possibility that's harder to dismiss. What if the silence isn't about caution or lack of interest? What if NASA and ESA are seeing something in the data that they don't understand and don't want to discuss until they have a better explanation? Institutional science is risk-averse. Announcing an anomaly before you can explain it is a career-damaging move. Far safer to stay quiet. Run more observations, double-check the calculations, and only go public once you have a complete story. Now let's talk about protocols. The International Academy of Astronautics has a set of guidelines called the Post-Detection Communication Protocols for dealing with potential technosignatures. These protocols outline what steps should be taken if a signal of possible extraterrestrial origin is detected. The key points are verification, consultation with other experts, and eventual public disclosure. But there's a built-in delay. The protocols emphasize that no announcement should be made until the detection is confirmed and the implications are understood. Has 3i Atlas triggered any of these protocols? We don't know. The protocols are designed for radio signals and deliberate transmissions, not for ambiguous behavior by a comet-like object. But some observers have speculated that the unusual characteristics of 3i Atlas might have prompted informal consultations among SETI researchers and planetary defense experts. If there's even a remote possibility that the object is artificial or carrying some kind of signal, those conversations would be happening behind closed doors. The Planetary Defense Coordination Office, part of NASA's Office of Planetary Defense, maintains a list of objects that warrant additional monitoring. This includes near-Earth asteroids with uncertain trajectories or unusual properties. 3i Atlas is not a near-Earth object in the technical sense, since it's not bound to the solar system, but some forum posts have claimed that it was briefly listed on internal watch lists used for training exercises or protocol development. Those claims are unverified. NASA has neither confirmed nor denied them, but if true, it would suggest that someone somewhere thought 3i Atlas deserved extra attention. Here's where psychology comes in. Humans are pattern-seeking creatures. We see connections and meanings even when none exist. When an institution stays silent, we fill the void with speculation. The absence of information becomes evidence of concealment. This is how conspiracy theories are born, not from malice, but from the gap between what we want to know and what we're told. December 15th has become a focal point in online discussions precisely because it's a data-specific concrete moment in time. If you're going to believe that something unusual is happening with 3i Atlas, you need a when. December 15th provides that when. It's close enough to feel imminent. It's specific enough to allow for predictions and preparations, and it's aligned with enough celestial geometry to sound plausible. Whether anything actually happens on that date is almost beside the point. The date itself has acquired meaning simply by being repeated enough times in enough contexts. I'm not here to tell you whether NASA is concealing something. I don't know. I can't know. But I can tell you that the structure of institutional silence creates conditions where doubt thrives. Every unanswered question becomes a seed of suspicion. Every delayed release of data becomes potential evidence of a cover-up. And every assurance that there's nothing to worry about paradoxically strengthens the belief that there's something to worry about. This dynamic is playing out right now in real time as December 15th approaches. The silence isn't breaking, the questions aren't being answered, and the countdown continues. Part 6: Lessons from the Visitors That Came Before. In October 2017, a University of Hawaii telescope scanning the skies for near-Earth asteroids caught something impossible. An object moving so fast and on such a steep trajectory that it couldn't be bound to our sun. The discovery team named it Oumuamua, a Hawaiian word meaning scout or messenger. That name would prove more prophetic than they realized. Oumuamua was unlike anything we had seen before. Its shape was inferred to be highly elongated, perhaps 10 times longer than it was wide. It showed no sign of a coma or tail, so it wasn't a comet in the traditional sense. But as telescopes tracked it over the following weeks, they noticed something strange. The object was accelerating. Not much, just a tiny extra push beyond what solar gravity alone would predict. That non-gravitational acceleration became the central mystery of Oumuamua. Scientists proposed various explanations. Maybe it was outgassing after all, but so faintly that we couldn't see the coma. Maybe it was being pushed by radiation pressure, sunlight bouncing off its surface. Maybe it was both, but none of the explanations quite fit the data. The acceleration seemed too strong for radiation pressure unless the object was incredibly thin and light. The absence of a visible coma made the outgassing hypothesis uncomfortable. And so the debates began. Some researchers, including Harvard astronomer Avi Loeb, suggested that Oumuamua might be artificial, a light sail, a probe, something built rather than born. The scientific community largely rejected that idea. Extraordinary claims require extraordinary evidence, and the evidence for Oumuamua being artificial was thin. But the controversy taught us something important. When an object behaves in ways we don't expect, we have to be willing to consider unconventional explanations not as the first resort, but as possibilities that remain on the table when conventional explanations fail. 2 years later, in August 2019, amateur astronomer Gennady Boris discovered a second interstellar visitor using a telescope he had built himself. This one was clearly a comet. It had a bright coma and a tail. Its composition, analyzed through spectroscopy, seemed similar to comets from our own solar system. Borisov was in many ways exactly what we expected an interstellar comet to look like, and that was reassuring. It suggested that Oumuamua might have been an outlier, an unusual case rather than a sign that we didn't understand interstellar objects at all. But even Borisov had surprises. Its carbon monoxide to water ratio was different from typical solar system comets. Its nucleus fragmented as it approached the sun, breaking into multiple pieces that dispersed along its orbit. And like Oumuamua, it exhibited non-gravitational acceleration due to outgassing. Though in Borisov's case, the mechanism was clear and uncontroversial. Now we have 3i Atlas, the third interstellar visitor. What does it teach us? First, that these objects are diverse. Oumuamua had no visible coma. Borisov had a strong coma. 3i Atlas shows extreme polarization and unusual dust properties. Each object is different and each challenges our assumptions in its own way. Second, that non-gravitational accelerations are common in interstellar objects. Both Oumuamua and Borisov exhibited them. If amateur observers are correct that 3I Atlas is also deviating from its predicted path, that would make 3 for 3. And third, that our detection and characterization capabilities are improving. We found Oumuamua only after it had already passed perihelion and was on its way out of the solar system. We found Borisov several months before perihelion, giving us time to study it. We found 3I Atlas even earlier with pre-discovery detections extending back to when it was still far from the Sun. This progression matters. Each interstellar object we detect teaches us more about what's out there and how to study it. But it also reveals how much we don't know. Before 2017, we had theories about interstellar objects but no direct observations. Now we have 3 examples and each one has raised as many questions as it answered. How common are objects like Oumuamua? Where do they come from? How long do they spend in interstellar space before encountering a star? Are there objects out there that are even more exotic than what we've seen so far? The history of these 3 visitors also reveals patterns in how the scientific community and the public respond. With Oumuamua, there was initial excitement followed by intense scrutiny and then controversy. With Borisov, there was interest but less drama because it fit expectations better. With 3I Atlas, we're still in the early phase. The data is incomplete. The interpretations are preliminary. But the seeds of controversy are already being planted by those amateur observations and trajectory anomalies. If December 15th passes without incident, 3I Atlas will probably join Borisov in the category of interesting but not shocking. If something unexpected happens, even something small, it could become the next Oumuamua, a source of debate and speculation that persists for years. There's a lesson in all this about humility. Each of these objects has reminded us that the universe is under no obligation to conform to our models. We build theories based on the data we have, but the data we have is always incomplete. Interstellar objects spend millions or billions of years crossing the void between stars. They experience environments and conditions that we can barely simulate in laboratories. When they arrive in our solar system, they bring with them information about processes and compositions that might be rare or absent in objects born here. The real question isn't whether 3I Atlas will surprise us. It's whether we're ready to be surprised. Whether we have the instruments, the funding, the attention, and the intellectual flexibility to recognize something truly novel when it appears. Oumuamua slipped away before we could get a really good look at it. Borisov gave us more time but still left unanswered questions. 3I Atlas is still here, still observable, still approaching its moment of closest alignment. We have an opportunity. Whether we use it wisely remains to be seen. Part 7. When amateur eyes see what professionals won't. There's a quiet revolution happening in astronomy, and it's not being led by billion-dollar space telescopes or government agencies. It's being led by people with backyard observatories, modified digital cameras, and a passion for watching the sky. These amateur astronomers are not professionals. They don't have PhDs or research grants, but they have something else: time, dedication, and freedom from institutional constraints. When 3I Atlas was announced in July 2025, the amateur community mobilized immediately. Within days, observers around the world were tracking the comet, measuring its position, recording its brightness, imaging its coma and tail. Some used sophisticated equipment, others used relatively simple setups, but all of them shared their data online in forums and databases where anyone could access it. And that's when the discrepancies started appearing. Let me explain how astronomical position measurement works. When you photograph a celestial object, you're recording its location against the background stars. If you know the exact coordinates of those background stars, you can calculate the coordinates of your target. This process is called astrometry. It sounds simple, but it's full of potential errors. Your telescope might not be perfectly aligned. The atmosphere might be refracting light. Your camera sensor might have distortions. Any of these factors can introduce errors of several arcseconds or even arc-minutes. Professional observatories account for these errors with careful calibration. They use reference catalogs of star positions measured to millisecond precision. They correct for atmospheric refraction using models of temperature and pressure. They average multiple observations to reduce random noise. The result is position measurements accurate to within a fraction of an arcsecond. Amateur observers, generally speaking, can't achieve that level of precision. Their typical uncertainty is larger, maybe 5 to 10 arcseconds. So when an amateur reports that 3I Atlas is offset from its predicted position by several arc-minutes, we have to ask, is that real, or is it measurement error? An arc-minute is 60 arcseconds. That's 10 times larger than typical amateur uncertainty. It's hard to explain an arc-minute offset as pure measurement error, unless something went seriously wrong with the observation. But it's also hard to explain as a real deviation unless the comet is experiencing extremely strong non-gravitational forces. Here's where it gets interesting. Multiple amateur observers using different equipment at different locations have reported similar offsets, not identical but correlated. They're seeing the comet displaced in the same general direction relative to the ephemeris predictions. That correlation is harder to dismiss as random error. When independent measurements agree even if they're noisy, it suggests they're capturing something real. The question is what one possibility is that the ephemeris itself is wrong. The official predictions from JPL horizons are based on orbital elements derived from early observations when the comet was still far away. If those initial measurements had small errors, or if the orbit calculation didn't properly account for non-gravitational accelerations, the predicted position could drift away from the true position over time. By December, that accumulated error could be substantial. Another possibility is that 3I Atlas is indeed experiencing non-gravitational accelerations that weren't included in the initial orbit solution. Comets are notorious for this. As they outgas, they create jets of material that push the nucleus in unpredictable direction. The effect is usually small, but it accumulates over time. For a highly active comet like 3I Atlas appears to be, the accelerations could be significant enough to cause noticeable deviations. Let's do some math. Suppose 3I Atlas has a non-gravitational acceleration of 10⁻². That's a tiny acceleration, about 1/1,000,000th of Earth's surface gravity. Over the course of a month, that acceleration would change the comet's velocity by about 26 ms. Over 2 months, from perihelion to December 15th, it would change the velocity by 52 p2 ms. That velocity change translates into a position offset. Using simple kinematics, an acceleration of 10⁻5 ms acting for 60 days produces a displacement of about 500,000 kilometers. At the distance of 3I Atlas, that corresponds to an angular offset of roughly 5 arcminutes. So an arcminute scale deviation is actually plausible if the comet is experiencing moderate non-gravitational acceleration. The question is whether that acceleration is included in the official orbit solution. If it is, then the amateur observations are either erroneous or indicating something beyond normal cometary behavior. If it's not, then JPL needs to update their ephemeris with better force models. Now let's talk about photometry. This is the measurement of an object's brightness. Amateurs have been tracking 3I Atlas's brightness since discovery, and some of them claim the light curve doesn't match predictions. Specifically, they report that the comet is fading more slowly than expected as it moves away from the sun, or that it's showing unexpected brightening episodes. Predicting comet brightness is notoriously difficult. It depends on the size of the nucleus, the amount of dust and gas being released, the reflectivity of those particles, and the geometry of observation. Professional models use empirical formulas calibrated on past comets. But every comet is different. Some follow the formulas, others don't. So a mismatch between predicted and observed brightness isn't necessarily alarming. It might just mean this comet is more or less active than average. But here's the nuance. If the brightness deviations are systematic, if they show patterns that correlate with the comet's position or orientation, that could indicate something interesting. For example, if the comet brightens whenever it's oriented in a particular direction relative to Earth, that might suggest a directional outburst or a reflective surface feature. That's the kind of detail that only emerges from careful continuous monitoring by many observers. The amateur community is doing that monitoring. They're creating light curves with nightly or even hourly resolution. They're comparing notes, cross-checking measurements, debating interpretations, and they're doing it all in public on forums and social media where anyone can follow along. This openness is both a strength and a weakness. It allows for rapid sharing of information and collaborative problem-solving, but it also allows errors and misunderstandings to propagate quickly. So here's where we stand. The amateur observations suggest anomalies. Position offsets, brightness variations, tail structure changes. Some of these might be real, some might be artifacts. The challenge is separating signal from noise. Professional astronomers have the tools and expertise to do that separation, but they're not always paying attention to what amateurs are reporting. There's a gap between the two communities, a disconnect in communication and trust. Amateurs feel like professionals are ignoring their data. Professionals feel like amateurs are jumping to conclusions without proper calibration. December 15th is a chance to bridge that gap. If the alignment produces any observable effect, the amateurs will be watching. They'll record it, measure it, and share it instantly. If nothing happens, they'll document that too. Either way, their observations will become part of the historical record of 3I Atlas. And maybe, just maybe, they'll catch something the professionals missed. Part 8. The physics of the impossible. Let's talk about forces. Everything that moves in space is pushed or pulled by something. Gravity is the obvious one. The sun's gravity shapes the orbits of planets and comets. Earth's gravity holds the moon. But gravity isn't the only force in play. There's radiation pressure, the momentum carried by photons of light. There's the solar wind streams of charged particles blowing outward from the sun. There's electromagnetic interaction, the way magnetic fields and electric currents push on each other. All of these forces act on comets, and all of them can cause deviations from purely gravitational trajectories. For most comets, the dominant non-gravitational force is the rocket effect from outgassing. When ice sublimates on the sunward side of a comet's nucleus, it turns into gas and expands rapidly. That expanding gas carries momentum. If the nucleus is rotating and the outgassing is stronger on one side than the other, the net momentum creates a thrust. It's like a leaky balloon spinning as it deflates. The effect is small, but over weeks and months it adds up. We can estimate the magnitude of this force. Take a comet nucleus with a radius of 1 km and a density of 500 kilos per meter outbury. That's about 2 trillion kilos of mass. If it's sublimating water ice at a rate of 1,000 kilos and the gas escapes at 500 mXs, the thrust is about 500,000 newtons. Divide the force by mass and you get an acceleration of about 2.5. 7 mXs. That's incredibly small, but it's not zero. Over 60 days, that acceleration produces a velocity change of 1.3 mXs and a position displacement of about 34,000 kilometers. At the distance of 3I Atlas from Earth, 34,000 kilometers corresponds to an angular offset of roughly 13 arcseconds. That's measurable, but it's within the noise of amateur observations. To get the arc-minute scale offsets that some observers are claiming, you'd need accelerations 10 or 20 times larger. That would require either much stronger outgassing or some additional force. Could outgassing be that strong? Possibly if the comet is unusually active. Remember that pre-discovery data showing activity at 6.5 astronomical units. That's far beyond where water ice normally sublimates. To be active at that distance, the comet would need to be rich in more volatile ices like carbon monoxide or carbon dioxide. These substances sublimate at much lower temperatures, and when they sublimate, they produce strong outgassing. There's another possibility. Suppose the comet's nucleus is rotating rapidly and has an irregular shape. The outgassing would be highly symmetric, concentrated in certain regions and pointing in specific directions. If those directions happen to align such that the thrust is consistently perpendicular to the Sun-comet line, the acceleration could change the comet's trajectory in unexpected ways. This is exactly what happened with Oumuamua. The non-gravitational acceleration couldn't be explained by uniform outgassing. It required some asymmetry, some preferred direction. Now let's consider electromagnetic effects. Comets have ion tails made of charged particles. Those particles interact with the interplanetary magnetic field carried by the solar wind. The interaction can create electric currents and magnetic forces. Could those forces be strong enough to push the nucleus? Probably not. The ion tail mass is tiny compared to the nucleus mass. Even if the ions experience large forces, the momentum transfer back to the nucleus would be negligible. But the ions themselves could be deflected, creating tail structures that don't point exactly away from the sun. That could affect how we measure the comet's center of light, potentially introducing apparent position offsets. There's a more exotic possibility: plasma interactions. The solar wind is a magnetized plasma, a soup of charged particles threaded with magnetic field lines. When a comet's coma and tail move through that plasma, they disturb it, creating waves and instabilities. Under certain conditions, those instabilities can produce localized electric fields and currents. Could such fields affect the trajectory of the nucleus? It seems unlikely, but it's not impossible. If the nucleus accumulated a net electric charge, and if the surrounding plasma had the right structure, there could be a small electric force. The magnitude would depend on details. We don't know the charge, the field strength, the plasma density. What about gravitational anomalies? Could there be some unseen mass near 3I Atlas that's perturbing its orbit? A small asteroid or a fragment of the nucleus itself? The perturbation force would scale with the mass of the unseen object and the inverse square of the distance. To produce noticeable effects, you'd need either a large mass very close or a moderate mass somewhat close. But if there were another object nearby, we'd likely see it. Our surveys are good at finding things. So this explanation seems weak unless the object is unusually dark and small. Let's step back. What are we really trying to explain? We're trying to explain why some amateur observers claim to see position and brightness anomalies. But before invoking exotic physics, we should consider the simpler explanation. Maybe the anomalies aren't real. Maybe they're artifacts of measurement error, calibration mistakes, or wishful thinking. That's the null hypothesis. The burden of proof is on those claiming anomalies to demonstrate that their observations are robust and reproducible. If the anomalies are real, then we need a physical mechanism. Asymmetric outgassing is the most likely candidate. It's well established. It happens in many comets. It can produce the right magnitude of effect. But if outgassing doesn't fully explain what's being observed, we start having to consider less conventional ideas. Plasma interactions, charge accumulation, fragmentation. Each step takes us further from the comfortable territory of textbook physics and into the realm where we're making educated guesses. And if none of those work, if we exhaust conventional explanations and still can't account for the observations, then we're in uncharted territory. That's when scientists start proposing really speculative ideas. That's when papers get written with titles like Anomalous Acceleration of Interstellar Object 3I Atlas Implications for Composition and Activity. That's when the conferences get interesting. But we're not there yet. We're still in the phase where most scientists think the observations are probably wrong, and the physics is probably normal. December 15th will be the test. If the alignment produces something measurable, something that can't be explained away as error or noise, then the conversation changes. Until then, it's all speculation. Part 9. Signals from the Silent Universe. In 1974, humanity sent a message into space. The Arecibo radio telescope in Puerto Rico transmitted a sequence of ones and zeros toward the globular cluster Messier, 1325,000 light-years away. The message encoded basic information about humans, our biochemistry, our appearance, and our solar system. It was mostly symbolic. The signal won't reach its destination for 25 millennia, and even if anyone receives it and responds immediately, we won't hear back for another 50,000 years. But the act of transmission was significant. It said we're here. We're intelligent and we're listening. We've been listening ever since. The search for extraterrestrial intelligence, or SETI, has used radio telescopes around the world to scan the sky for artificial signals. The idea is straightforward. If another civilization wants to communicate across interstellar distances, radio waves are an efficient way to do it. They travel at the speed of light. They're not blocked by dust or gas. And certain frequencies like the 1.42 GHz line from neutral hydrogen are universal beacons that any technological species would recognize. For decades SETI has listened, and for decades we've heard nothing but silence. Oh, there have been candidates' brief signals that looked interesting: the WOW signal in 1977, BLC-1 in 2020. Each time excitement followed by disappointment when the signal didn't repeat or turned out to have a terrestrial explanation. The silence is so profound that some scientists have started asking whether we're looking in the right way. Maybe radio isn't how advanced civilizations communicate. Maybe they use lasers or neutrinos, or some method we haven't even imagined. Or maybe they're not trying to communicate at all. Enter the idea of technosignatures. Instead of listening for deliberate transmissions, we look for signs of technology. Megastructures that block starlight, industrial pollution in exoplanet atmospheres, waste heat from energy consumption, and relevant to our discussion. Interstellar probes. Objects that travel between stars carrying instruments, power sources, and possibly communication equipment. Could 3i Atlas be such an object? Let's think through what that would require. First, a power source. Solar panels would work near a star, but in interstellar space they'd be useless. Nuclear power could be an option. A kilogram of enriched uranium can provide about 24 million kilojoules of energy. That's enough to run a modest spacecraft for years. Alternatively, radioisotope thermoelectric generators, the kind used on Voyager and Cassini, can provide steady power for decades. Second, a communication system to transmit across interstellar distances. You need either high power, a large antenna, or both. The power required scales with distance squared at 1.6 astronomical units from Earth. Where 3i Atlas will be on December 15th, the distance is about 240 million kilometers. To send a detectable signal over that distance with a 1-meter antenna, you'd need roughly 10 watts of transmitter power. If you're using a narrow beam and a sensitive receiver, that's feasible. A laptop uses more power than that, but here's the catch. Why would an interstellar probe wait until it's aligned with Earth to transmit? If it's been traveling for millions of years, why does the geometry matter? One answer is efficiency. If the probe has limited power and wants to maximize the chance of detection, it would wait until it's close to the target star and in a good geometric position. Transmitting during alignment reduces the required power and increases the signal-to-noise ratio. It's like waiting for a clear line of sight. Another answer is triggering. Maybe the probe is programmed to activate when it detects certain conditions: the presence of a technological civilization, radio emissions from the target planet, or simply a favorable geometric alignment that indicates it's time to announce its presence. This is all speculation, of course. We have no evidence that 3i Atlas is anything other than a comet, but the speculation is grounded in plausible engineering. What would a signal from 3i Atlas look like? It depends on what the sender wants to convey. A simple beacon would be a repetitive pulse at a specific frequency modulated in a way that screams artificial. Think prime numbers, mathematical constants, or a patterned sequence that couldn't arise naturally. A more complex message might encode information, images, text, or data about the sender. The challenge is making it comprehensible to a receiver who doesn't share your language or mathematics. SETI researchers have thought about this problem for decades. The consensus is that any civilization capable of building an interstellar probe would be smart enough to make their signal obviously artificial. They'd use redundancy, error correction, and universal concepts that transcend culture. If we received such a signal from 3i Atlas on December 15th, we'd know it. The pattern would be unmistakable. But here's the unsettling part. What if the signal isn't meant for us? What if 3i Atlas is a relay passing messages between distant nodes of a network that spans the galaxy? In that case, we'd be eavesdropping on a conversation we're not part of. The signal might not be designed for easy interpretation. It might be encrypted or compressed in ways that make it look like random noise to us. We'd see the carrier wave, the evidence that something was being transmitted, but we wouldn't understand the content. That scenario is simultaneously fascinating and frustrating. It would confirm that we're not alone. It would prove that interstellar communication is possible and happening, but it would also make us feel like outsiders, primitives, watching the adults talk without being invited to the table. Is that better or worse than silence? I honestly don't know. There's one more angle to consider. What if 3i Atlas isn't transmitting but reflecting? Imagine a distant civilization that wants to communicate with us but doesn't want to wait 50,000 years for a round-trip message. They could use an interstellar object as a mirror. They send a signal toward it timed so that it arrives when the object is aligned with Earth. The object reflects the signal, and we receive it. The advantage is speed. Light from the source to the reflector might take years, but once it bounces, it reaches us in minutes. The total communication time is much shorter than a direct transmission. For this to work, the reflector would need to be highly reflective at the right frequencies and oriented correctly. That's a lot of requirements, but if you're a civilization capable of interstellar engineering, maybe it's doable. Maybe you seed your galaxy with reflectors positioned, so that you can communicate with emerging civilizations as they develop radio astronomy. December 15th could be one of those communication windows, a moment when Earth 3i Atlas and some distant transmitter align just right. I want to be clear, I don't believe 3i Atlas is an alien probe. I don't think it's going to transmit on December 15th. The evidence for such extraordinary claims is non-existent, but the scenario illustrates something important about how we search for intelligence in the universe. We're not just listening for hello. We're watching for anything that doesn't fit the pattern, anything that suggests intention, design, purpose. And when an interstellar object does something unexpected, even if that something has a perfectly natural explanation, our minds leap to the possibility that we're seeing the fingerprints of another mind. That impulse, that hope or fear, is deeply human. It's what drives SETI forward despite decades of silence, and it's what makes December 15th feel significant even if it's not. Part 10. The machine that learns to see the strange. There's an astronomical survey that began operations in 2023 called the Vera Rubin Observatory. When fully operational, it will photograph the entire visible sky every few nights, creating a time-lapse movie of the universe. Every supernova, every asteroid, every variable star, every transient event will be captured. The data volume is staggering 15 terabytes per night. Over its 10-year mission, it will generate something like 500 petabytes of images. No human could possibly look at all that data. Even a team of thousands of astronomers working around the clock couldn't keep up, so we're training machines to do it for us. Machine learning algorithms, neural networks, AI systems, these technologies can recognize patterns in astronomical images faster and more reliably than any human. These systems are already deployed on existing surveys. They flag supernovae, detect asteroids, classify galaxies, and they're getting better every year. One of the most interesting capabilities of these AI systems is anomaly detection. The idea is simple: you train the algorithm on examples of normal objects, stars, galaxies, comets that behave according to known physics. Then you turn it loose on new data and ask it to flag anything that doesn't fit the pattern, anything weird, anything anomalous. The algorithm doesn't need to understand what the anomaly is or why it's happening, it just needs to recognize that this object is not like the others. This approach has already led to discoveries: unusual stellar variability galaxies with bizarre structures, transients that don't match any known category. It's particularly useful for objects like 3i Atlas, a comet that shows activity far from the Sun, has extreme polarization, and possibly deviates from its predicted trajectory. These are exactly the kinds of features an anomaly detection algorithm would flag. Imagine an AI system trained on light curves of thousands of comets. It learns what a normal brightness variation looks like as a comet approaches and recedes from the Sun. Then it's shown the light curve of 3i Atlas. If that curve has features that don't match the training data, unexpected bumps, dips, or slopes, the algorithm raises a flag. A human astronomer then looks at the flagged case and decides whether it's genuinely interesting or just a quirk of the data. This is happening right now, not specifically for 3i Atlas, but for the broader population of solar system objects, and it's changing how we discover and study things. We're no longer limited by human attention and bias. The machines don't care if an object is famous or obscure. They don't get bored looking at the 10,000th light curve. They just process data and flag outliers. In a sense, they're better observers than we are. But there's a flip side. AI systems can be fooled. They can mistake instrumental artifacts for real signals. They can overfit to their training data and miss genuinely novel phenomena that don't resemble anything they've seen before. And they're black boxes. When a neural network flags something as anomalous, it can't always explain why. It just outputs a probability score. The human astronomer has to interpret what that means. So here's a scenario. In late November 2025, a machine learning system analyzing observations of 3i Atlas detects an anomaly. Maybe it's a sudden brightness fluctuation that doesn't fit the standard cometary activity model. Maybe it's a shift in the tail orientation that suggests a change in outgassing direction. Maybe it's a subtle positional offset that accumulates over multiple nights. The algorithm flags it. The flag gets reviewed and the reviewer has to make a decision. Is this real or is this noise? If it's real, what happens next? Ideally, follow-up observations, point more telescopes at the object. Get higher resolution images, measure spectra. Try to characterize the anomaly and understand its cause. But telescopes are a limited resource. You can't just drop everything to observe one object unless you're sure it's important. So there's a judgment call. How confident are you that the anomaly is genuine? How interesting would it be if it is? And how much are you willing to bet of your limited observing time on a maybe? This is where December 15th enters the picture. If the anomaly detection system flags something unusual about 3i Atlas, in the weeks leading up to the alignment, that flag takes on added significance. It's not just an anomaly in isolation. It's an anomaly that might be building towards something, a trigger, an event, a climax. That narrative makes it more compelling, more worthy of follow-up, even if the underlying science is uncertain. Now, expand this beyond 3i Atlas. We're entering an era where AI systems will be constantly monitoring the sky, flagging anomalies, generating alerts. Some of those alerts will be false positives, some will be real but mundane, and some, a tiny fraction, will be genuinely new phenomena that change our understanding of the universe. The challenge is sorting them out, deciding which alerts to take seriously and which to ignore. In a way, the machines are extending our senses. They're allowing us to see patterns and changes that would be invisible to unaided human observation. But they're also creating new kinds of uncertainty. When a human astronomer discovers something, they can describe what they saw and why they think it's interesting. When an AI flags something, all you get is a number, a confidence score. You have to trust that the algorithm is doing something sensible even though you can't fully inspect its reasoning. December 15th is a test case for this new paradigm. If multiple AI systems trained on different datasets and using different architectures all flag 3i Atlas as anomalous in the days before the alignment, that's a strong signal. It suggests there's something real happening, something that transcends individual measurement errors or algorithmic quirks. On the other hand, if the flags are inconsistent or if they disappear when the data is carefully checked, that tells us the anomalies were probably artifacts. Either way, we'll learn something about how to use these tools, how to balance machine insight with human skepticism, how to navigate a universe where discovery is increasingly mediated by algorithms we don't fully understand. Part 11. The Politics of Planetary Defense. In 2013, a 20-meter asteroid entered Earth's atmosphere over Chelyabinsk, Russia, and exploded with the force of about 500 kilotons of TNT. The shockwave shattered windows across 6 cities. Over 500 people were injured, mostly by flying glass. The asteroid was undetected before impact. We had no warning, no time to evacuate, and no ability to deflect or destroy it. The Chelyabinsk event was a wake-up call. It demonstrated that Earth is vulnerable and our detection systems have gaps. In response, space agencies around the world expanded their near-Earth object monitoring programs. NASA established the Planetary Defense Coordination Office, PDCO. The United Nations endorsed the creation of the International Asteroid Warning Network, IAAWN, and the Space Mission Planning Advisory Group, SMPAG. These organizations coordinate observations, assess risks, and plan potential mitigation missions. Their job is to make sure Chelyabinsk doesn't happen again, or if it does, that we see it coming. But there's a tension at the heart of planetary defense. How do you communicate risk to the public without causing panic? If you detect an asteroid that has a 1% chance of hitting Earth in 10 years, do you announce it immediately? Do you wait until the probability is better constrained? Do you say nothing and handle it quietly? There's no consensus. Different agencies have different policies, and those policies are constantly being debated and revised. Enter 3i Atlas. It's not a near-Earth object in the technical sense. Its closest approach to Earth is 1.8 astronomical units, far beyond the threshold that defines a potentially hazardous asteroid. But it is an interstellar visitor, and we don't have much experience with those. Oumuamua raised questions about how to classify and communicate information about such objects. Should they be treated like asteroids, like comets, or like something entirely new? Some observers have speculated that 3i Atlas was briefly included on internal watch lists used by planetary defense organizations. Not because it poses an impact threat, but because its unusual behavior makes it worth monitoring more closely. These watch lists are often confidential. They're used for training exercises, protocol development, and coordination among agencies. Objects are added and removed based on evolving assessments. The public rarely hears about them unless something escalates to a formal warning. If 3i Atlas were on such a list, what would that mean? Probably nothing dramatic. It would mean that someone somewhere thought the object's trajectory or characteristics were uncertain enough to warrant extra attention. Maybe they wanted to practice their observation protocols. Maybe they wanted to test how quickly they could gather data and refine an orbit. Maybe they were just being cautious. But in the world of conspiracy theories, inclusion on a watch list becomes evidence of hidden danger, proof that authorities know more than they're saying. There's also the question of disclosure protocols for potential technosignatures. The post-detection protocols developed by the SETI community outline steps to take if a signal of possible extraterrestrial origin is detected. Key principles include verification before announcement, consultation with relevant experts, and eventual public disclosure. But these are guidelines, not laws. There's no enforcement mechanism, and they were written primarily for radio signals, not for ambiguous behavior by physical objects. If 3i Atlas were exhibiting behavior that suggested an artificial origin, who would decide whether and when to announce it? NASA, ESA, the International Astronomical Union, the United Nations. The answer isn't clear, and that ambiguity creates space for speculation. If no announcement is made, is it because there's nothing to announce or because the announcement is being delayed, while experts debate what it means? The broader context is important here. We're living in an era of heightened distrust of institutions. Government agencies, scientific bodies, media organizations all face skepticism from significant portions of the public. When those institutions say nothing to worry about, many people hear they're hiding something. This dynamic plays out in pandemic responses, climate science, and space weather forecasting, and it plays out with 3i Atlas. But from a policy perspective, the challenge is balancing transparency with responsibility. Too much transparency too early can lead to misunderstanding and fear. Too little transparency too late can erode trust and fuel conspiracy theories. The ideal is to provide accurate, timely information in language that the public can understand. But achieving that ideal is difficult when the science itself is uncertain and evolving. December 15th sits at the intersection of all these tensions. It's a specific date, a moment when something might or might not happen. If agencies have been tracking anomalies in 3i Atlas's behavior, December 15th would be a natural checkpoint, a time to see if the predictions hold, or if something unexpected occurs. If something does occur, even something small and explainable, the pressure to disclose will be immense. Social media will light up. Amateur observers will share their data. The story will spread whether officials want it to or not. On the other hand, if nothing happens, the silence will be interpreted in multiple ways. Skeptics will say, "We told you so," dismissing the speculation as baseless. Believers will say the event was covered up, or that the real effects are being concealed. And the agencies themselves will likely say nothing, preferring to let the non-event fade from public attention without comment. What I find fascinating is how this situation reveals the limits of our current governance structures for dealing with cosmic phenomena. We have protocols for known threats like asteroids. We have protocols for potential signals. But we don't have protocols for ambiguous situations where an object is behaving strangely but not threateningly, where the science is uncertain but the public interest is high, where the line between natural phenomenon and artificial object is blurry. December 15th might force us to develop those protocols, or it might just become another footnote in the long history of cosmic false alarms. Either way, it's a learning moment. Part 12. When the sun throws a tantrum. The sun is not a stable, well-behaved star. It's a roiling ball of plasma threaded with magnetic fields that twist and snap like rubber bands stretched too far. Every now and then, those magnetic fields release their stored energy in explosive events called solar flares and coronal mass ejection (CMEs). These eruptions fling billions of tons of charged particles into space at speeds ranging from several hundred to over 1,000 km/h. When those particles reach Earth, they interact with our magnetic field, creating geomagnetic storms. Most of the time, these storms are minor. They produce pretty auroras, and maybe cause some radio interference, but occasionally they're severe. In 1859, the Carrington event, the largest geomagnetic storm in recorded history, caused auroras visible as far south as the Caribbean, and set telegraph systems on fire. If a storm of that magnitude hit today, it could damage satellites, disrupt GPS, and knock out power grids across entire continents. The challenge is prediction. We can see CMEs leaving the sun and estimate when they'll arrive at Earth, usually within a few hours. But predicting their impact is harder. The strength of a geomagnetic storm depends on the orientation of the magnetic field embedded in the ejected plasma. If that field aligns opposite to Earth's field, it couples efficiently and creates a strong storm. If it aligns parallel, the coupling is weak and the storm is mild. We can't measure the field orientation until the plasma reaches satellites positioned between the Sun and Earth about an hour before impact. That's not much warning. In 2025, the Sun is near the peak of solar cycle 25. Activity levels are high, with flares and CMEs being frequent. Space weather forecasters are kept busy issuing alerts and watching for big events. And here's where it gets interesting. What if around December 15th we experience an unexpected geomagnetic storm? What if a coronal mass ejection arrives at Earth at the same time? 3i Atlas is in alignment. How would we distinguish a solar origin disturbance from a hypothetical effect caused by the comet? The answer is, we probably couldn't, at least not immediately. Both scenarios would produce similar signatures: enhanced auroral activity, fluctuations in Earth's magnetic field, increased radiation levels detected by satellites, and disruptions to radio communications. The timing would be suspicious, but timing alone doesn't prove causation. Correlation is not causality. Even if a geomagnetic storm coincides exactly with the December 15th alignment, it could be pure coincidence. But let's dig deeper. Solar storms have structure. They have rise times, peak intensities, and decay patterns that follow known physics. The storm's characteristics depend on the speed and magnetic configuration of the coronal mass ejection that caused it. Space weather scientists can often trace a storm back to its solar source, identifying which flare or eruption produced it. If a storm arrives on December 15th, and we can clearly identify its solar origin, that settles the question. It's solar, not cometary. However, what if the storm characteristics don't quite match the identified solar event? What if the intensity is stronger than expected, or the magnetic field orientation is unusual, or there are secondary peaks that don't fit the standard profile? Then we're in ambiguous territory. Maybe our solar wind models are incomplete. Maybe there was additional acceleration of the plasma en route, or maybe there's a contribution from another source. I want to walk you through a scenario. It's speculative, but it's physics-based. Suppose 3I Atlas's ion tail contains magnetic structures, flux ropes, created by the interaction between the comet's outflowing plasma and the interplanetary magnetic field. These structures are moving outward from the comet at the solar wind speed roughly 400 km/s. On December 15th, Earth is downstream of the comet at a distance of about 1.6 to 1.8 astronomical units, or 240 million km. At 400 km, material released from the comet would take about 7 days to reach Earth. Now suppose that around December 8th, a week before alignment, the comet experiences a sudden increase in activity, an outgassing burst or fragmentation event at something that releases a large amount of ionized material into its tail. That material gets caught up in the solar wind and is carried toward Earth. By December 15th, when the geometric alignment is perfect, that enhanced plasma reaches Earth's magnetosphere. Simultaneously, the Sun happens to launch a coronal mass ejection. It's not aimed directly at Earth, but it's close enough that its flanks brush our magnetosphere. The two effects, solar and cometary, arrive at the same time and combine. The result is a geomagnetic disturbance that's stronger or more complex than the solar contribution alone would produce. Could we detect the cometary contribution? Maybe. If we had spacecraft monitoring the solar wind upstream of Earth, they might detect compositional anomalies. The comet's plasma would have different abundances of elements and isotopes compared to solar plasma. It might have higher carbon or nitrogen content. It might show spectral signatures of cometary molecules. If instruments were looking for those signatures, they might find them. But here's the problem: we're not looking. The spacecraft we have in the solar wind are designed to monitor solar emissions, not cometary contributions. They measure bulk plasma properties like density, velocity, and magnetic field. They don't routinely analyze detailed composition, so the cometary signature, if it exists, might go unnoticed. The storm would be attributed entirely to the solar event, and December 15th would pass without anyone realizing that 3I Atlas had made a small but measurable contribution to Earth's space weather. That's the frustrating thing about ambiguous events. Even if they happen, even if they produce real effects, they can be masked by other phenomena, or overlooked because we're not set up to detect them. Science is not a perfect observer. We see what our instruments are designed to measure, and we interpret what we see through the lens of our models and expectations. If an effect falls outside that framework, it can be invisible. There's one more angle to consider: false positives. Space weather prediction is an imperfect science. Sometimes forecasters predict a strong storm and nothing happens. The coronal mass ejection misses Earth, or its magnetic field orientation is unfavorable, or it dissipates en route. Other times a storm arrives with little warning because the solar eruption was on the far side of the Sun and only became visible as it crossed into Earth's line of sight. If forecasters predict enhanced geomagnetic activity for December 15th and it doesn't materialize, what does that mean? It could mean the prediction was wrong. Or it could mean something else. Maybe the predicted solar storm was real, but it was counteracted or deflected by plasma from 3I Atlas. Maybe the alignment created a shielding effect that reduced the storm's impact. Again, this is highly speculative, but it illustrates how difficult it is to interpret null results. The absence of an expected effect can be as mysterious as the presence of an unexpected one. Here's my point. December 15th sits in a space weather environment that's already complex and unpredictable. The Sun is active. Coronal mass ejections are frequent. Earth's magnetosphere is constantly buffeted by variable solar wind. Against that noisy background, detecting a subtle contribution from an interstellar comet would be extremely challenging. It's like trying to hear a whisper in a crowded room. Even if the whisper is there, even if it's saying something important, you might miss it. That doesn't mean we shouldn't try. Space weather monitoring networks are more sophisticated than ever. We have satellites, ground-based magnetometers, radar systems, and auroral cameras all feeding data into real-time analysis systems. If something unusual happens on December 15th, it will be recorded. The question is whether anyone will notice it at the time, or whether it will only be discovered later when researchers go back through the archives looking for anomalies. And that brings me to a sobering thought. How many strange events have already happened that we missed? How many times has the universe whispered to us and we didn't hear? We only discover what we're looking for, and we only look where we expect to find something. Everything else slips through the cracks. December 15th might be one of those cracks, or it might be the moment we finally pay attention. Part 13: Fast Radio Bursts and the Mystery of Cosmic Static. In 2007, astronomers analyzing archival data from the Parkes Radio Telescope in Australia found something that shouldn't exist. A pulse of radio waves lasting just a few milliseconds but carrying as much energy as the Sun emits in an entire day. The pulse showed a characteristic dispersion pattern where different frequencies arrived at slightly different times, indicating it had traveled through vast amounts of ionized gas. The conclusion was inescapable: this pulse had come from far outside our galaxy from a distance of billions of light years. They called it a fast radio burst, FRB. At first it seemed like a fluke, A single detection could be an instrumental artifact or terrestrial interference. But then more were found, dozens then hundreds. Some repeated, most didn't. Their origins remained mysterious. Magnetars, superdense neutron stars with intense magnetic fields, were one leading candidate. Colliding black holes were another, and inevitably some suggested they could be artificial signals from extraterrestrial civilizations, pulses from interstellar communication networks, evidence that we're not alone. The artificial hypothesis is considered fringe by most astronomers. Natural explanations seem adequate to explain the observed properties. But here's the thing, we don't actually know what causes them. Every natural model has problems. Every attempt to explain the observed diversity of characteristics requires special circumstances or fine-tuning. The mystery persists, and mysteries have a way of generating speculation. Fast forward to 2025. FRB detections are routine. Observatories around the world have instruments dedicated to finding and characterizing them. The catalog has grown to thousands of events. Some of those events are genuinely strange. Repeating bursts that show periodicity, suggesting they originate from a rotating object. Bursts with complex subpulse structures that hint at multiple emission regions. Bursts that cluster in time, appearing in groups separated by months of silence. Now imagine this, and on December 15, 2025, as 3I Atlas reaches its alignment with Earth, radio telescopes detect a fast radio burst. The timing is coincidental, right? FRBs happen all the time. On any given day, multiple FRBs are detected somewhere in the world, so finding one on December 15th wouldn't be remarkable. Unless the FRB has unusual properties, unless its dispersion measure, the parameter that indicates how far it traveled, suggests an origin that's inconsistent with a distant extragalactic source. Unless its arrival direction, when triangulated by multiple observatories, points uncomfortably close to the position of 3I Atlas in the sky. That would be harder to dismiss as coincidence. The probability of a random FRB appearing from the direction of 3I Atlas at the exact moment of alignment would be very small. Not zero, but small enough to raise eyebrows. And if the FRB had other unusual features, if it repeated with a pattern that suggested intelligence, the eyebrows would shoot even higher. Let me be clear about probabilities. The sky contains about 40,000 square degrees. If FRBs occur uniformly across the sky, at a rate of a few per day, the probability of detecting one from any particular square degree region on any given day is about 1 in 10,000. 3I Atlas occupies a tiny fraction of a square degree, so the prior probability of a coincidence is genuinely tiny. If it happens, it demands explanation. But here's where it gets tricky. FRB detection is not uniform across the sky. Observatories have preferred pointing directions based on their observing schedules. And on December 15th, if amateur and professional astronomers are all watching 3I Atlas because of the alignment hype, radio telescopes might also be pointed in that direction, not to search for an FRB, but to look for radio emission from the comet itself. And if you're looking at a particular patch of sky, you're more likely to detect an FRB from that patch simply because you're watching it. That selection bias complicates the interpretation. Was the FRB really associated with 3I Atlas, or did we just happen to catch a random FRB because we were looking in that direction? Disentangling those possibilities requires careful statistical analysis, and probably data from multiple observatories that weren't focused on the comet. There's another scenario worth considering. Suppose 3I Atlas itself emits a radio pulse. Not a fast radio burst in the technical sense, because those are extragalactic, but a transient radio signal. A burst of electromagnetic radiation triggered by some event in the comet's coma or tail. Plasma instabilities can generate radio waves. Lightning discharges in dusty cometary environments have been proposed but never definitively observed. If such a discharge occurred in 3I Atlas during the alignment, it might produce a detectable radio signal. The signal would be much weaker than an FRB, because it's coming from a nearby object, not from billions of light-years away. But at a distance of 1.6 astronomical units, a moderately powerful emission could still be detectable by sensitive radio telescopes. This signal would have different characteristics than an FRB, no dispersion or very little, because the radio waves wouldn't have traveled through intergalactic space. A broader frequency range, less narrow band, possibly longer duration. If radio astronomers detect such a signal on December 15th, it would be a genuine discovery, evidence of a new type of cometary activity, a mechanism for electromagnetic emission that isn't included in current models. The science papers would be fascinating, but it wouldn't be evidence of intelligence or artificial origin. It would just be physics we didn't know comets could do. The challenge is that detecting radio emission from comets requires knowing where and when to look. Most radio telescopes are pointed at distant galaxies, quasars, and pulsars. Pointing them at a comet is unusual. It only happens if someone specifically requests it, and telescope time is precious. So unless there's a compelling reason to observe 3I Atlas at radio wavelengths on December 15th, the observation probably won't happen. But here's where the online speculation could actually help. If enough astronomers are talking about December 15th, if the alignment date becomes widely known in the community, someone might decide to point a radio telescope at the comet just to see what happens. It's the kind of thing a graduate student might do with a few hours of observing time on a smaller instrument, check for radio emission, rule it out, or discover something new. Low risk, potentially high reward. So there's an interesting feedback loop. Speculation drives observation, which generates data which either confirms or refutes the speculation. In the best case, we learn something new about comets. In the worst case, we gather more data that adds to our understanding even if it's null results. Either way, the speculation has value if it motivates actual scientific investigation. And that perhaps is the real significance of December 15th. Not that anything dramatic will happen, but that people are paying attention. That an otherwise routine astronomical event has captured enough imagination to drive serious scrutiny. The universe is full of wonders that go unnoticed because no one is looking. This time at least people are looking. Part 14. The question that changes everything. Let me take you back to basics. Back to the fundamental question that underlies all of this speculation, all of this analysis, all of this anticipation. The question is not what 3i Atlas will do to Earth. The question is, are we alone? Every search for anomalies, every speculation about artificial origins, every hope that December 15th might bring something unexpected traces back to that deeper question. We've been asking it for as long as we've looked up at the stars. Ancient philosophers wondered if other worlds existed beyond our own. Medieval scholars debated whether God would create life elsewhere in the cosmos. 20th century scientists built radio telescopes to listen for signals. And now in 2025 we're watching an interstellar visitor and wondering if it's carrying a message. The statistics suggest we shouldn't be alone. Our galaxy contains somewhere between 100 and 400 billion stars. Recent exoplanet surveys tell us that most stars have planets, potentially habitable worlds, planets in the right temperature zone to support liquid water number in the billions just in the Milky Way. The universe has had 13.8 billion years to generate life, intelligence, and technology. The raw materials are abundant. The time is sufficient. So where is everybody? That's the Fermi paradox, named after physicist Enrico Fermi, who posed it during a casual lunch conversation in 1950. If intelligent life is common, we should see evidence of it: megastructures, radio signals, probes, visiting our solar system. The absence of such evidence, the great silence, is one of the deepest mysteries in science. Maybe life is rare. Maybe intelligence is rare. Maybe civilizations destroy themselves before they become spacefaring. Maybe they're out there but hiding. Maybe they're here and we don't recognize them. 3i Atlas is a test case for one version of that last hypothesis. If advanced civilizations use interstellar objects as carriers for probes or communication devices, then every object that enters our solar system from interstellar space is potentially significant. We can't dismiss any of them without careful examination. Oumuamua taught us that its strange acceleration, its unusual shape, its failure to outgas, all of these features are still not fully explained. Mainstream science has settled on natural explanations involving hydrogen ice or exotic cometary compositions. But a minority of researchers, including respected astronomers, maintain that artificial origin remains a viable hypothesis. With 3i Atlas, we have a second chance, a second opportunity to apply everything we learned from Oumuamua: better instruments, more observers, earlier detection. If there's anything artificial about this object, we have a better chance of finding it than we did with Oumuamua. And December 15th, with its alignment geometry, represents a natural experiment, a moment when any deliberately timed signal or effect would manifest. But I want to shift perspective for a moment. Suppose we're wrong. Suppose there's nothing artificial about 3i Atlas. Suppose December 15th comes and goes with no anomalies, no signals, no unexpected effects. What does that tell us? Does it mean we're alone? Of course not. It means one interstellar comet out of 3 detected objects wasn't artificial. That's hardly a comprehensive survey. The search for extraterrestrial intelligence is a long game. It might take centuries. It might take millennia. Or it might happen tomorrow when a radio telescope catches an unmistakable signal, when a probe reveals itself, when something occurs that leaves no room for doubt. We don't know the timescale. We don't know the odds. We just know that if we stop looking, we guarantee we'll never find anything. December 15th matters not because it's likely to produce a dramatic revelation, but because it represents a specific testable moment. We can point our instruments. We can gather data. We can analyze and interpret. If something happens, we document it. If nothing happens, we document that too. Either result advances our knowledge. Either result narrows the space of possibilities. There's something profound about standing on a planet, hurtling through space, watching an object from another star system pass nearby, and asking whether it might be carrying a message from beings we've never met. It's an act of optimism, of hope, of reaching beyond the boundaries of our experience towards something greater. Even if the answer is no, even if we're talking to ourselves in an empty room, the act of asking changes us. It reminds us that we're part of something larger than our individual lives, or even our entire civilization. The astronomer Carl Sagan once said that the cosmos is within us, that we're made of star stuff contemplating the stars. He was right, but it goes deeper than chemistry. We're a way for the universe to know itself. And if there are others out there, other minds asking the same questions, looking at the same stars, then we're connected to them through that shared curiosity, through the simple act of wondering. 3i Atlas is just rock and ice. Probably, almost certainly. But even if it's just a comet, it's a comet that came from somewhere else. It carries information about a different part of the galaxy, about the composition of interstellar clouds, the formation of planetary systems, the processes that shape matter across light years and eons. That information is valuable. That story is worth hearing. And if against all odds, against all reasonable expectation, it turns out to be more than rock and ice, if December 15th brings something we didn't anticipate, then everything changes. Not just our science, not just our technology, but our understanding of our place in the cosmos, our sense of who we are and what we might become. That's what's really at stake. Not our physical safety. Earth will be fine regardless of what 3i Atlas does or doesn't do. But our cosmic loneliness, our philosophical isolation, the question of whether we're the universe's only attempted self-awareness or one among many. December 15th won't answer that question definitively, but it might give us a clue, a hint, a direction to look. And sometimes that's enough. Part 15. The Vigil. So here we are. It's the days leading up to December 15th, 2025. Around the world, telescopes are trained on a patch of sky where 3i Atlas drifts on its hyperbolic path. Amateur astronomers are checking their equipment, calibrating their cameras, planning their observation schedules. Professional observatories are running routine surveys that will capture the comet along with thousands of other objects. Space weather forecasters are monitoring the sun for coronal mass ejections. Radio astronomers are listening to the cosmos for fast radio bursts and unexpected signals. Most of these people expect nothing unusual. They're doing science, gathering data, following protocols. December 15th is just another date on the calendar, another night of observations. But some of them are wondering, some are watching with a little extra attention, a little extra hope or fear or curiosity, wondering if this might be the night something changes. Let me tell you what to watch for if you want to follow along. First, space weather. NOAA operates a space weather prediction center that provides real-time data on solar activity and geomagnetic conditions. Their website shows current solar wind parameters, geomagnetic indices, and forecasts. If Earth's magnetosphere experiences unusual disturbances on December 15th, it will show up in those data streams within hours. Look for spikes in the K-index, a measure of geomagnetic activity. Look for aurora reports from latitudes where they're not normally visible. Look for satellite operators reporting anomalies or communication disruptions. Second, positional data. JPL Horizons provides ephemeris predictions for 3i Atlas that you can access online. If you have access to observations, either your own or shared by others, you can compare measured positions to predicted positions. Any persistent offset larger than a few arc minutes confirmed by multiple independent observers would be significant. Forums like the Minor Planet mailing list and amateur astronomy communities on Reddit are places where such observations get shared and discussed. Third, photometry. Light curves showing 3i Atlas as brightness over time are being compiled by amateur observers. If the comet shows unexpected brightening, dimming, or fluctuations on December 15th, those will appear in the photometry data. The trick is distinguishing real variations from measurement noise and atmospheric effects. Multiple independent measurements that show correlated behavior are more convincing than single reports. Fourth, radio observations. This is harder for casual followers because radio telescope data isn't usually publicly available in real time. But SETI organizations and some university radio observatories occasionally post updates about their observations. If a significant radio transient is detected from the direction of 3i Atlas, it will probably be announced within days through astronomers' telegrams or similar channels. Fifth, social media and news. If anything genuinely unusual happens, word will spread quickly. Scientists will tweet. Forum discussions will explode. News outlets will pick up the story. The challenge is separating signal from noise in that information stream. Many claims will be exaggerated or misinterpreted. Some will be outright false. Critical thinking and source verification are essential. Now, what are the realistic outcomes? The most likely scenario is that December 15th passes quietly. 3i Atlas continues on its predicted trajectory. Its brightness fades as expected. No radio signals are detected. Space weather remains within normal bounds. Amateur observers see nothing anomalous, and gradually over the following weeks interest wanes. The speculation is forgotten. 3i Atlas becomes a footnote. Another interstellar visitor that came and went without drama. That would be the null result. Disappointing to those who hoped for something more, but scientifically valuable nonetheless. Null results tell us that our models are working, that we understand comets well enough to predict their behavior, that interstellar objects, at least these three we've detected, are natural phenomena requiring no exotic explanations. The second scenario is minor anomalies, small deviations from predictions, a brief geomagnetic disturbance that might or might not be related to the alignment, an unexplained brightening episode that lasts a few hours, amateur position measurements that show offsets just barely above the noise level. These kinds of ambiguous signals would generate debate but not revolution. Scientists would argue about interpretations. Some would say the anomalies are real and interesting. Others would say they're artifacts or coincidences. Papers would be written. Conferences would have sessions, but no consensus would emerge. The third scenario, the dramatic revelation, is the least likely but most impactful. A clear, unambiguous signal. a radio pulse that repeats with mathematical precision, a brightness variation that encodes information, a positional deviation so large it can only be explained by propulsion, satellite disruptions that correlate perfectly with the alignment timing and can't be attributed to solar activity. In this scenario, we'd have genuine evidence that 3I Atlas is not entirely natural. The scientific response would be swift follow-up observations with every available instrument, emergency meetings of international space agencies, activation of post-detection protocols, and inevitably public disclosure. You can't keep something like that secret. Which scenario will play out, I don't know. Nobody knows. That's why December 15th matters. It's a genuine unknown, a roll of cosmic dice. And whether the dice come up ordinary or extraordinary, we'll have learned something. But here's what I want you to remember. The significance of December 15th isn't really about what happens on that specific date. It's about what it represents. A moment when humans around the world are looking outward together, watching an object from another star system, asking questions about its nature and origin. That collective attention, that shared curiosity is rare and precious. Most days, most people are focused inward on immediate concerns, local problems, personal lives, and that's fine. That's necessary. But occasionally we need to look up to remember that we're part of something vast, strange, and wonderful. 3I Atlas has given us a reason to look up. Whether it's just a comet or something more, it's connected us to the larger cosmos in a tangible way. It's reminded us that space is not empty, that objects cross between stars, that our solar system is part of a dynamic galactic neighborhood. And it's prompted us to ask whether we're alone, whether anyone else is out there watching their own sky, and wondering the same things. Those questions don't get answered on December 15th. They get answered over decades and centuries through patient observation, rigorous analysis, and occasional lucky discoveries. December 15th is just one data point in that long search, but it's our data point, our moment, our chance to watch and wonder. So watch if you can, follow the space weather reports, check the astronomy forums, look at the data as it comes in, and ask yourself what you hope to see. Do you hope for the confirmation that we understand the universe and everything is proceeding according to natural law? Or do you hope for the surprise, the anomaly, the revelation that we're not alone, and the cosmos is stranger than we imagined? Either way, December 15th is coming. The countdown has already begun. 3I Atlas is approaching its alignment, and somewhere out there crossing the gulf between stars, a visitor from another system is about to have its closest conversation with Earth. Whether that conversation is silent or speaks volumes, we're about to find out.